Hello, everyone, and welcome to today's live broadcast, Freeze Drying Solutions for Your Lab, presented by Megan Zimerman, Product Manager, and Jenny Sprung, Senior Application Specialist, Labconco Corporation. I'm Sarvi Greneman of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is brought to you by LabRoots and sponsored by Labconco. For more information on our sponsor, please visit labconco.com. Now let's get started. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click on the Send button. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the window, click on the arrows at the top right-hand corner of the slide window. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Ask a Question box located on the far left of your screen. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located at the top right of the presentation window and follow the process to obtain your credits. I'd like to now introduce our presenters, Megan Zimerman and Jenny Sprung. Megan Zimerman is a product manager for Freeze Dryers and Evaporators at Labconco Corporation. She has a BA in biology. Prior to joining Labconco, she spent several years in laboratory working on research in pediatric, gastroenterology, and agricultural sciences. Jenny earned her degree in biology with minor in chemistry from the University of Wisconsin, Parkside, graduating in 1997. Prior to starting at Labconco, she worked at SC Johnson Wax and Sensory Marketing. After graduating, she started in an R&D laboratory working with cleaning products for the home. In 1998, she moved to Kansas City and started working with Labconco in the marketing department as a product specialist. She was promoted to a product manager position overseeing the development of evaporation, lyophilization products, and glassware washer lines. Currently, she is a senior application specialist with emphasis on evaporation and lyophilization, glassware washers, water, and forensic products, but she also covers all Labconco's 17 product lines. Megan, you may now present your presentation.
Today we'll be talking about freeze drying solutions for your lab. We'll start by discussing a general overview of the freeze drying process, followed by how to select a freeze dryer to meet your needs. Then I'll pass things off to Jenny, and she'll talk about how to develop a protocol, freeze drying challenging samples, and troubleshooting. First, we'll start by discussing some common terms you might hear in freeze drying. Freeze drying is the process of removing moisture from a frozen product using a vacuum. Another term you might hear is lyophilization, which is just another word for freeze drying that is derived from the Greek word solvent-loving. Lyophilized samples are easily rehydrated, making it a great process for sample preparation because you can easily resuspend your samples. Sublimation is also a word you'll hear when talking about freeze drying. This is the process in freeze drying in which solvents pass directly from a solid phase to a gas phase, giving freeze-dried samples such great preservation properties because you are bypassing the liquid phase. The rate at which sublimation occurs is dependent on temperature and pressure. This graph shows what's happening to your sample when you freeze dry. For sublimation to occur, you need to have a cold enough temperature and a deep enough vacuum for your sample to go from a solid to a gas. If either of these things doesn't occur, the sample will actually evaporate and not get the preservation properties that you would during sublimation. So pressure and temperature are critical components of freeze drying. When freeze drying, it is important to cool the material below its triple point, which is shown on the graph. The triple point is the highest temperature at which the solid and liquid phases of material can coexist. Being below this point ensures that sublimation rather than evaporation will occur. Next, we are going to talk about the requirements needed for the freeze drying process. The first requirement is that you must have a pre-frozen sample before you start your run. When you put the frozen sample on the freeze dryer, it will be subject to melting until the appropriate vacuum level is established. You might see this melting occur with older vacuum pumps or pumps that aren't working well because it will take longer for the vacuum to pull down. So the vacuum level and how quickly it pulls down are critical to the freeze drying process. Another requirement of freeze drying is that you need a collector that is 15 to 20 degrees colder than the sample's freezing point. By nature, water molecules from your sample will want to move to the coldest spot in the system, the condenser coil. This natural migration of water molecules is called cryopumping. The next requirement for freeze drying is having a deep vacuum, with a minimum requirement of 0.002 millibar. This is necessary because the vacuum pump establishes negative pressure, forcing free-flowing water molecules that have left the sample by sublimation to evacuate from the environment around the sample and travel to the condenser coil. The last requirement for freeze drying is having energy in the form of heat. While not obvious to a lot of people, the lyophilization process is essentially a heat transfer process. For example, with flask freeze drying, the flask is hanging at room temperature and the ambient heat from the room is what's driving the process. In general, the more heat you are able to apply to your samples, the faster your run will go. However, not all samples can take the same amount of heat input. If you add too much heat to certain samples, you could cause your sample to melt. These images show the difference between uncontrolled heat and controlled heat. With uncontrolled heat, the flask is receiving ambient heat from the air in the room, making it hard to control. For samples in the pharmaceutical industry or production samples, people will typically use a tray dryer so they can apply controlled heat to their samples. When you're freeze drying, there are 3 stages that occur. First is the pre-freezing stage, where you start with a completely frozen sample. This is followed by primary drying and then secondary drying. For many laboratories, there isn't much difference between these 2 stages, but for pharmaceuticals or for more sophisticated freeze dry runs, there is a very distinct difference. On this graph, it's showing a freeze dry run throughout the 3 stages of the process. The blue line shows the shelf temperature, while the green line shows the temperature of the sample. The graph begins showing the freezing of the product, and when the sample matches the shelf temperature, freezing of the sample has occurred. This stage is then held for a while to ensure the entire sample is completely frozen. After the hold, you see the shelf temperature start to climb in primary drying. However, the sample temperature no longer correlates to the rise in shelf temperature. This is because the sample is undergoing evaporative cooling, which suppresses the temperature. This is also what allows you to add heat during primary drying. With the addition of this heat, you are increasing the rate of sublimation and shortening your runs. Primary drying continues until your shelf temperature and sample temperature meet. For most laboratories that are planning to resuspend their samples, this is the point when they would typically end the run, with their samples containing about 7 to 8% moisture. However, for end users who are preparing their samples for long-term preservation, they will continue their run into secondary drying. Secondary drying is where water molecules that are bound to a sample are released. With the additional heat in this last stage, you are able to drive those bound water molecules out of your sample and are left with about 2% moisture. For more sophisticated freeze drying, you can send your samples off to companies where they will watch the freeze drying process under a microscope. They can then tell you your sample's triple point and what amount of heat input would be good for your run. In general, most labs will just guesstimate the heat input, fine-tuning their process to develop an optimized lyophilization run. Now we are going to talk through each of the 3 stages in a little more detail. In the pre-freezing stage, if you are freezing your sample in a flask, you want to make sure you're freezing your sample in a way that gives you the greatest chance for efficiency during your run. The first example on the left shows stub freezing, which is just keeping your sample on a flat surface and is not a good way to freeze your sample. The example in the middle is called slant freezing, where you keep your sample at an angle while you freeze it. By doing this, you're increasing the surface area of your sample, which helps reduce your overall run time. The example on the right, shell freezing, is the most optimal way to freeze your sample, especially when you're working with large volumes. What shell freezing does is roll the sample while it is freezing in a very cold solution to create a thin coating over the entire surface of the flask. This gives you the largest surface area and reduces the amount of sample the water molecules have to move through during freeze drying. Once your sample is frozen and you start your freeze dryer, you begin primary drying. As you can see in the picture, there is so much evaporative cooling happening during this step that you will get frost buildup on the outside of your flask. This is a good indication that your freeze drying process is going well. If you see the frost start to melt, as well as your sample, this is indicating that there is a problem with your run. At this point, you are no longer freeze drying and your sample is undergoing evaporation. When we are able to control heat input in primary drying, the temperature your sample is at plays an important role in your run. While some samples can take a lot of heat, other samples don't do well with heat input. The example shown is from a paper where they were studying the effects of freeze drying the same sample at different temperatures. The example on the bottom left shows the result of a collapsed cake. A cake is what you call the remaining product after you freeze dry your sample. With this run, the sample melted and underwent evaporation instead of sublimation when the shelf temperature was set at -10 degrees Celsius and the product was at -15 degrees Celsius. The example on the bottom right shows the result of a partially collapsed cake. With this run, they adjusted their shelf temperature to -15 degrees C and had a product temperature of -20 degrees C. With the last example on the top right, they adjusted their shelf temperature to -20 degrees C with a product temperature of -25 degrees C and had a finished product with an excellent cake. So you can see that even though none of these runs had a difference of more than 5 degrees Celsius from one to the next, there was still a very big difference in how the final product turned out. This is why you will have to fine-tune your process to develop a protocol that will give you the best cake, unless you plan to send your samples off to be tested. After primary drying is complete, you move into secondary drying, where you are releasing the remaining water molecules that are bound to the sample. In order to complete secondary drying, you need a freeze dryer that has shelves so you can apply additional heat to your samples and get the moisture content down to about 2%. For long-term storage of your samples, you will want to complete secondary drying, and you'll want to also stopper or seal your samples under a vacuum. By stoppering your samples under vacuum, you avoid exposing your samples to the moisture in the air when you open the door. Another way to achieve long-term storage is to flame seal your samples in ampules before the vacuum is released. Next, I'm going to talk about selecting a freeze dryer that meets the needs of your lab. The first thing you'll want to think about is who all will be using the freeze dryer. Is this purchased just for your lab, or will multiple groups be using the freeze dryer? Find out what kind of samples each person plans to use the unit for, looking at the types of solvents and acids that make up their samples. Also determine who will be responsible for maintenance, such as cleaning the coils and performing oil changes on the vacuum pump. This will help to keep your freeze dryer and vacuum pump in optimal working condition. Choosing the right materials for your freeze dryer is important when making your selection. Many solvents used in samples can attack plastic and rubber components, which cause vacuum leaks over time. Because of this, it's important that you know what kind of solvents and acids everyone will be using, because you want to make sure the samples will be compatible with the materials of your freeze dryer. Other than knowing what kind of solvents will be used, you'll also want to determine the collector temperature you need, keeping in mind that the temperature should be 15 to 20 degrees colder than the freezing point of your samples. Freeze dryers typically come in collector temperatures of -50, -84, and -105 degrees Celsius. You also need to determine the collector size of your freeze dryer. Freeze dryers are described by their ice holding capacity. So if you're looking at a 4.5 liter freeze dryer, that means it can hold 4.5 liters of ice before needing to be defrosted. This does not mean that you can put 4.5 liters of sample on the freeze dryer, but instead you would put about half that volume on there to accommodate all the vapors that will come off your samples when you start your run. The next thing that you need to determine is the type of vacuum pump you need. Freeze drying requires that your pump be able to reach 100 microns with a displacement of at least 98 liters per minute. When selecting your freeze dryer, you also need to consider the accessories you'll need. Besides offering flasks and serum bottles, we also offer items like tube racks and microplate holders. With microplates, since you're working with such a small volume of sample, it's very easy for that sample to start melting quickly. With our microplate holder, you can place your microplate on the holder while you're freeze drying your sample and keep it on there during your run to help keep the sample frozen while your vacuum is cooling down. Another thing to consider when selecting a freeze dryer is the coil design. With our internal coil design, we are able to provide the coldest possible temperatures and are superior in capturing solvents coming off your samples compared to an external coil design that is on the outside of the condenser. Some other things to consider when selecting a freeze dryer. What kind of controls does your freeze dryer need? What do you need to get the appropriate data and results from your run? Do you need your freeze dryer to meet CGMP standards? Do you need a freeze dryer with shelves to pre-freeze your samples? When you're controlling your freeze dryer, what kind of software and programming do you need? How are you accessing your data? With our new LyoWorks software, you're able to download your data to a USB flash drive or use an Ethernet connection to send your run data straight to your computer through a one-way connection. We also offer remote notification with the ability to configure the types of alerts that are sent to your email. Since freeze dry runs can sometimes last for days, leaving you wondering how your samples are doing while you're away from the lab, you can have alerts sent to your phone showing you the parameters of the run, giving you some peace of mind while you're away. A vacuum control valve is another important feature to have in your freeze dryer. By being able to set the vacuum level, you're able to speed your runtime of certain solvents. Many people think if they pull the deepest vacuum, it will speed their run, but that isn't the case. Having your sample set at 0.2 millibar is actually the most efficient vacuum setting. Endpoint detection is another feature to consider if you're freeze drying in flasks. Oftentimes, it can be difficult to tell if your sample is done, which leads people to sometimes take their samples off too soon, only to realize the run wasn't complete and causing them to start the run all over. Or they are leaving their samples on for much longer than they really need, just to ensure that their run is finished, wasting time and energy the freeze dryer is using. Our endpoint detection helps you avoid both of these outcomes by alerting you to when your samples have achieved the level of dryness that you've set. Now I'm going to pass things over to Jenny, where she'll discuss developing a protocol.
Great. Thank you, Megan. Now we'll start talking about your specific protocols. This is a great opportunity for you to ask questions so that we can respond to you as we go through this process. When developing a protocol, as Megan mentioned, there are 3 steps. You have pre-freezing, primary drying, and secondary drying. As long as your samples are 100% frozen, you are ready to move on to primary drying. However, a lot of people feel like their samples are frozen, but they're really not ready to go on, and they'll start seeing meltback immediately. The protocol we're looking at on this slide is done in a tray dryer, which will do all 3 steps for you. You'll load your liquid samples, typically in serum vials or on bulk trays. You'll run the pre-freezing process at a set temperature. Once the samples are completely frozen, then you're going to start pulling a vacuum and adding a little bit of controlled heat to those samples to do your main drying process. From there, you go into secondary drying, which is still under vacuum, but adding additional heat. And then when the samples are done, you'll pull them off. You'll either stop or under vacuum, or you'll unload them through the door. If you're doing the process in flasks on a standard port-type freeze dryer, you'll pre-freeze either in a shelf freezer or in a standalone freezer, attach them to a port, pull a vacuum, and your heat is going to come from the room temperature. There's also heated product shelves that you can do this secondary drying part, but not the pre-freezing. So during the freeze-dry process, there are a lot of different options and different freeze dryers to choose from. It really depends on what you're trying to attempt as well as your budget. To optimize your lyophilization process, there's a few things that you can do. First of all, never overfill your container. If you have a 600 ml flask, you don't want to put more than about 200 milliliters into that flask. What this is going to allow is greater surface area of those samples for faster freeze drying. It's also going to prevent breaking the flasks during the pre-freeze process. So it will be helpful if you can just fill to 1/3 full. Also, many users will use test tubes inside of our flasks, and that's a great way to get your more surface area as well as run multiple samples inside of one flask. When you're looking at your different pumps, there are 3 different types to choose from. You have a standard pump, you have a hybrid pump, and you have a scroll pump. There's pros and cons to each and every one of those pumps, but to go over them briefly, typically the rotary vein pump is going to be for aqueous-based samples. The scroll pump will be for solvents and acids. And the scroll pump is a dry pump, so that can be used for pretty much anything, and it will not require oil changes. You do not need to oversize a pump, or you also don't want to undersize a pump. So keep that in mind. A lot of people think bigger is better, but that's not always the case in lyophilization. If you are unsure what size pump to use, feel free to give us a call and we're happy to help you. The pre-freeze step is actually the most important step in your freeze-dry process. You want greater surface area because the more surface area you get, the faster your freeze-drying will become. If you can shell freeze, that's the best way to do it. But another option is slant freezing, just in a standard freezer. Keep in mind that freeze-drying starts from the top down. Once that top layer is dry, it makes it more difficult for those molecules to move out. So you'll definitely want to get more surface area to prevent that. And you do want to pre-freeze to the sample's freezing point or lower. Again, you just want to make sure that that sample is 100% frozen. For the freeze-dry process, the rate of pre-freezing is very important. Fast pre-freezing can create small ice crystals, where controlled cooling can actually create larger ice crystals. The larger the ice crystals, the faster your freeze-dry process will be. So depending on what you want your outcome to be, if you're doing sample prep and you need this done quickly, fast pre-freezing might be preferred over a controlled rate freezing. If you want the samples to freeze-dry quicker, then you may want to do some controlled freezing with those samples. The next step, once your samples are 100% frozen, you want to go into primary drying. And the primary drying is going to take the longest portion of your freeze-dry process. During primary drying, many people think, especially when they're using a controlled shelf type system, that colder is better, but it's actually just the opposite. If you can add heat during that primary drying process, you're going to have faster dry times, and then you'll have faster secondary drying. So overall, the rate of that freeze-dried sample will go quicker if you can add heat. However, keep in mind, if you add too much heat, you're going to melt your sample, and the opposite is going to be true. So just watch for your samples, watch the melting. If they do melt, you can actually pre-freeze them again and start over in many cases. It's just very dependent on your samples. And you can also have control of your vacuum pressure. Sometimes if you have too deep of a vacuum, it does not allow those molecules to move out. So controlling your vacuum is an important lyophilization process as well. A lot of times when we see freeze dryers set up, they'll be in front of a window or in a tiny room, and it'll be very warm in that room because the freeze dryer is going to create some heat on its own. So you do need to make sure that you have ambient room temperature of about 22 degrees C. Make sure that the room is not too small. A medium-sized room is good. Make sure that your system is not set up in front of a very sunny window. So for example, if you live in the south and you're putting your freeze dryer in an alcove with a window in it where the sun is shining directly onto that freeze dryer, it's going to be very difficult for that freeze dryer to maintain its temperature, but it's also going to create meltback of your sample. During the winter, you don't want the unit under a heat vent because, again, you're blowing heat down onto a frozen sample, and that could have issues with meltback of your samples itself. If you are doing the pre-freeze step in a separate freezer, you don't want that freezer 3 buildings down where you have to walk 2 miles to get it to the freeze dryer, because obviously by the time it gets to the freeze dryer, it could be melted. So a couple things to keep in mind, and I have seen examples of all of these. So when I talk about these examples, they're not made up. They are real-life examples. Your final outcome, sometimes you get a very pretty powder, a pretty cake, or a pretty outcome, but sometimes you don't. every once in a while you'll need to add bulking agents or stabilizers. If your sample is prone to being degraded by freezing, you may have to use a lyoprotectant to help against that pre-freezing step. Next, we're going to talk a little bit about the cGMP requirements. And according to the FDA, if you want a cGMP piece of equipment, that's actually done on your end. So you can take the piece of equipment and make it fit the needs of your GMP requirements. What a manufacturer can do for you is we can offer you the materials of construction. We can give you the test reports that we have done on your freeze dryer based on your serial number to let you know that it did pass all of our internal QA specifications. We also offer all the manuals, the documents, the videos, everything that you need. We do IQ, OQ. We offer it at no charge. PQ would be done by an outside corporation that you would contact to come in to finish up your qualifications. But we are always happy to help in any of the steps and whatever you need to make sure that your freeze dryer can be used with your cGMP standards. There are multiple challenging samples, and as freeze drying evolves into a sample prep step versus a long-term storage step, we're seeing more and more challenging samples. One of them that I have seen is called tert-butyl alcohol. So on paper, tert-butyl looks like it should freeze dry fine. It has a great eutectic temperature. There should be no issues. However, when you actually freeze dry it, you don't get a nice powder. You actually get a gummy type sample. So very difficult to reconstitute. You may have issues keeping it dry because you've already kind of got that gummy wet that you can't get totally dry. So as a sample prep step, the tert-butyl is fine as long as you're going to use it right away, but obviously for long-term storage, it's already starting to rehydrate, so you're going to have issues with that long-term. Another product that is very difficult to dry are alcohols. Alcohols such as ethanol and methanol have a very low freezing temperature. And as Megan noted, you must have a temperature differential between your collector and your sample's freezing point of about 20 degrees. So for example, ethanol has a freezing point of minus 117 degrees, which would mean that you would need a freeze dryer of minus 137 degrees. There's not a freeze dryer out there that can go that low. So how do you get around if you need to freeze dry freeze dry ethanol samples? What you'll do is you must use a minus 105 freeze dryer, and you must dilute those samples to 10% or less. 10% is the spot that we have found in our testing where that sample does not melt back, but it does go through the freeze-dry process. So 10% is your magic number whenever you're doing alcohol-based samples, and you have to have a minus 105 degree freeze dryer. DMSO is another solvent that we're seeing more and more often. DMSO is difficult because that solvent, just the solvent alone, is going to start attacking rubber and plastic components. And anytime you have anything under vacuum, such as a lyophilizer, it's got to use rubber components for the gaskets and the O-rings to keep that under a deep vacuum. So what we recommend with DMSO is it will freeze dry fine. Just watch all of your rubber and plastic components and replace as needed. We've also found that sugars and salts cause a lower eutectic temperature, so we do recommend a cascade model. We also have seen with samples such as fruit that the sugars bypass the collector and they could get into your pump. So a HEPA filter in line with the pump is recommended. Again, with soil samples, and we do recommend a HEPA filter with those as well, because what happens with soil samples is during the dry process, they could become very powdery, and they're going to bypass the collector and go right into the vacuum pump. So be very careful with soil samples. They're great. They freeze dry very nicely. Same with leaves, tissues. They freeze dry nicely. Just watch the composition of those samples. If you need a HEPA filter to protect the pump, that's something that can be easily added in line. If you have whole fruit samples or whole animal samples, such as fish, it's best to either homogenize the fruits and vegetables, or if you can poke holes in the tissues of your animals or poke holes in the fruit. If you're freeze drying, for example, grapes or blueberries, poking holes through those skins will be helpful. A big part of freeze drying is going to be troubleshooting. If your samples won't stay frozen during the freeze dry process, there's a couple things that you can look at. Make sure that you have the correct freeze dryer. As Megan mentioned, you must have a temperature differential between the freeze dryer and the sample's eutectic temperature. For example, with acetonitrile, which has a eutectic temperature of -42, you must have a freeze dryer that is -62 degrees or colder. In this case, we would recommend a Cascade model, which reaches -84 degrees. If your samples are small or in plastic containers, those tend to melt a lot quicker, even walking from your freezer to your freeze dryer. And if your samples have alcohols in them, alcohols have a very low freezing point, which require a -105 degree freeze dryer, as well as diluting those alcohols to 10% or less. Also take a look at the pressure of your freeze dryer, because if your pump is not pulling correct pressure, that could also lead to melting back of your samples. Sometimes a sample can be very lightweight or very powdery, and they'll get pulled out by the vacuum. So using filter paper or parafilm is a way around that. You'll still notice that your samples might pop up in the tube, but if you can put some parafilm over, at least you won't lose your samples. If your samples are taking a long time to lyophilize, your shelf temperature might be too cold, your sample may be too thick, or you might be somehow blocking a vial. If you have a vial inside of a flask, you may not have enough headspace to encourage those molecules to leave your vial. A couple things to check. If you're noticing that you're having a vacuum level that's not what it used to be, make sure none of your gaskets have cracks in them or any dirt on them. Sometimes we'll see dust or dirt on the gaskets, and even little specks of it can prevent pulling a deep vacuum. So check your gaskets, check all of your valves, and always do an oil change. If you're unsure when the last oil change was, it's probably time to do another oil change. Oil changes really are dependent on how often you use the freeze dryer, as well as what solvents you're using in your freeze dryer, because if solvents are bypassing getting into your pump, you will have issues. We also recommend doing a purge on your pump before and after running your freeze dryer. If your samples are not sealing correctly, and this would be in terms of a tray dryer where you're going to be stoppering under vacuum, you need to make sure that you have your vials evenly distributed on the shelf to make sure that you can get good stoppering. If the final product looks different each and every time, there's a couple reasons for that. Different room temperatures, so if you're going from a summer run to a winter run, obviously your room temperatures are going to be a little bit different, as well as the dryness in your air. So that can actually affect the outcome of your sample, how pure your solvents are going in, and the percent of your active ingredient. That can all change the outcome of your sample. If you want a cake versus a powder, you do have to watch kind of what you're doing. If you are using different types of solvents, some people choose to use a keeper solvent with these to make sure that they look fine coming out. But it's really a matter of trial and error and what you're trying to get as an outcome. Equipment maintenance, the number one thing to watch for on your freeze dryer is your vacuum pump. The freeze dryer will alert you after 1,000 hours to do an oil change, but some people may need to do an oil change after each run, but it's very dependent on your solvents and how well you're keeping up with your freeze dryer and the maintenance on the freeze dryer itself. A hybrid pump is a 2-in-1 pump. So the hybrid pump is actually going to be cleaning out the oil during the run, where a scroll pump is going to be an oil-free pump. So the maintenance is very minimum, and there are no oil changes for a scroll pump. A rotary vane pump is a standard pump. It's the pump that most people are familiar with, but they do require more oil changes. The pump that you're looking at right here is a pump that was run on a freeze dryer with water samples only. However, the user never did an oil change. The samples were melting back, and the water got into the pump and was allowed to sit in the vacuum pump for a long period of time, creating the rust that you're looking at. Obviously, that pump is not fixable at this point, but this is very common, and this is what can happen to your pump if you don't perform enough oil changes. When I mentioned that we recommend a purge, that's where the gas ballast comes into play. So anytime you have an oil pump, there's a gas ballast on that pump. Typically, you're going to see the gas ballast settings for 0, 1, and 2. During a run, you want the gas ballast set at 0 to get full vacuum. But when you're done with the system and you shut it down and your samples are all removed, you want to get that system vacuum tight, put the gas ballast to 2, and run that pump at full speed for about 15 minutes after the process. That's going to do what we call a purge, and it's going to purge the contaminants out of your oil by leaking air into that oil, allowing that oil to get really hot, and getting rid of those contaminants. That will save the life of your pump. That is it for the presentation. If there are any questions, we would love to hear from you, and now's the time to ask them.
Thank you, Megan and Jenny, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many questions as we have time for. Let's get started. Our first question is, you mentioned optimum pressure is 0.2 mbar. What shelf temperature is optimal, and are the two related?
That's a great question. We do discuss the optimal pressure in terms of your specific sample types. So depending on what you're doing, typically aqueous-based 0.2 millibar is a great starting point. In terms of the shelf temperature, what you do need to keep in mind is what your specific sample is. So again, if it's aqueous samples, then you would want to set the shelf temperature to just below your eutectic temperature or your freezing point in terms of the primary drying, so when you're initially starting. But as you go into the secondary drying, you can actually add a little bit more heat to continually drive off the sample, the rest of the moisture. So it's really very dependent on what your specific sample is. Again, for aqueous samples, you probably want to start it at maybe -5, but if you're looking at more of a, say, an HPLC sample that has some acetonitrile in it that will have a freezing point of -42, if you start it too high, you're going to melt back that sample. So it's very dependent on your specific sample in order for us to give you kind of an idea of where to set that shelf temperature at. I'm happy to help you with your specific sample offline if you want to email one of us, or I can shoot you an email as well.
Thank you for that answer. The next question is for Jenny. Jenny, I have a new lyophilizer and have not gotten it set up yet. If I have a question, can I contact you later?
Absolutely. Yep, we're always here for you. Just email or call. We also have live chat if you prefer to do live chat. So however you want to do it, I am happy to help you.
Thank you. And the next question is, will my current vacuum pump work with Labconco Freeze Dryer?
That's always a good question, and it really, we would need to know the specifications on that pump. If it's a diaphragm-based pump, it will not work, so it must be a rotary vane-based pump or a scroll pump. And one thing that I always remind people is that the pump gets plugged into the actual freeze dryer itself, so you can use it in automatic mode. If the plug does not match with our plug, then you'll have to plug it into the wall, and automatic mode will not work.
Great. Thank you for that answer. The next question is, how can I seal under vacuum without buying a stopper-ring tray dryer?
That's a really great question. Stopper-ring tray dryers are used for individuals that are freeze drying really large volumes of samples. So we do offer a few other options that include our mini stopper-ring chamber and a clear stopper-ring chamber that are used for just if you're doing maybe a handful of serum bottles, as well as our ampule pod. With the ampule pod, you would connect that to a port on your manifold, like if you were using a flask. And then when those samples are finished, before you release your vacuum, you would flame seal the ampule closed to keep it ready for long-term storage.
Okay, great. Thank you. Our next question is, how does end zone endpoint detection work?
So with our end zone endpoint detection, this is used when you're freeze drying in flasks, and you're able to take an empty port on your manifold and insert a probe into that port, and then you take a separate probe and insert it into your freeze dry flask through the lid, and then before you start your run, you set a level of dryness, so a user-selected level. And when the level of dryness has been achieved, you are alerted through email that your samples are finished.
Great. Thank you. Our next question is, we find from time to time differences on the appearance of the cakes within a run. What can be done? What can be the reason of that?
Megan, do you have this one?
It's up to you.
All right. Yeah, my phone actually just blacked out, so I just want to make sure that I can hear you. Okay. So you're talking about the cracked cakes, is that correct?
I don't know, but I believe that's what they are asking, yes.
Okay, great. So when you're freeze drying, you have to keep in mind that you may or may not get the same outcome each and every time, depending on where that sample is located. If it's on a shelf, and say you have some of those samples on a shelf towards the middle of the shelf, which are going to be more insulated, or towards the front of the shelf where you're going to get more UV light, so you're going to get more radiant heat on those samples, you may get a different outcome each and every time. It could also be the difference between if you have too much, if you have more active in one sample than in another sample, that could also have a different outcome. So it's normal to see a cracked cake. I know it's not as pretty as a nice powdery cake, but that is normal. And typically when you check the sample's activity after the process, you'll find that the activity is the same.
Great. Thank you. Let me ask you, what special precaution should be taken to lyophilize the enzyme solution samples?
Okay, so in terms of your specific enzyme, and as you'll notice, everything is very specific to your sample. So when I'm talking, it's kind of a general overview, but your specific sample, it will depend. Now, some enzymes can be freeze sensitive, which means that they get damaged during the pre-freeze process. So you will want to use a lyoprotectant in that case to protect those enzymes. Some enzymes are fine being frozen and there's no issues, but they may have a heat issue after the sample is freeze-dried and you're going into secondary drying. So you really do need to know your enzyme and what it can and cannot handle in terms of lyophilizing.
Okay. And then what are the main reasons for some cracked cakes being along with good cakes? Anything to do with the shelf?
Well, yep, and I actually answered that one earlier. It really is dependent on the outcome, and it looks like we've had that question multiple times. So what I think might be the best is if possible, I will email each of you who have asked that question, and we can talk more specifically about your samples themselves.
Okay, great. Thank you again, Megan and Jenny. Do you have any final comments for our audience?
We really just want to thank everybody for taking the time to call in today.
Thank you. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today or those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. We would like to thank LabRoots and our sponsor, Labconco, for underwriting today's educational webcast. This webcast can be viewed on demand through January of 2019. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Thank you, and until next time, goodbye.